Alright, what's up guys? This is Matthew Burns, and this is probably going to be the final tutorial in this series, as the last thing we have to cover is the programming. I probably should explain what you are looking at right now is actually going to be part of this project. I'm not going to do a tutorial on this because this is not really related to, well, not related too much to electronics and programming and assembly or anything like that. But I am writing a piece of code in Python so that I can just through this graphical user interface here design my image, and then I want this this Python program to I guess export or save a text file with the assembly code. The reason why I want something to do that is because I need to have 96 different bytes, all the general purpose file registers for the red, green, and blue for a 16 by 16 display. So 32 reds, 32 greens, and 32 blues bytes of data in the general purpose registers, and drawing the images just by going through the file, going through the assembly text file and editing the zeros and ones by hand is very complicated, and oftentimes I end up with the image backwards or upside down, or maybe I put the top half on the bottom or the bottom half on the top, and it's just a mess. So I want something that's clean, and I just have to figure out how to do it once, and then the program will just keep doing it for me again and again and again. Every time I want to change the image, all I have to do is draw something on this program, or one thing I plan to implement at some point is importing an image, having it converting the image to a 16 by 16 kind of thing, picking the best color out of the ones I have available, and then exporting that, I guess, as the assembly file. So this isn't done yet, though. It's just something I'm working on. What this tutorial is on, what I should be going over instead of this, is this here. Now, the software I'm using to program my microcontrollers is a program called, I'm having trouble with the camera, MPLab. There's the desktop icon right there. You can download a copy of it from Microchip. If you just open up an Internet Explorer page. I apologize for not having a good desktop recorder, but I don't. I looked all over the place. I couldn't find one. If you have any recommendations, please comment, because I would like to know. Don't ask why I had that taped to my screen. So if you just Google MPLab, just Google MPLab actually, and it'll be a download from Microchip's website. Now they have this MPLab X out, this new version. I've tried it, and I'm sure it's great, but I honestly have no clue what I'm doing with it. So I use MPLab, one of the versions of version 8 or whatever. So, yeah, you just pretty much download it from this website. As far as writing the assembly code goes, I'm not going to go through all the details of using MPLab, but basically when you open it up, you are going to get a page that looks very similar to this. You won't see that. You'll just see this window in the upper left-hand corner of MPLab, this window here, and you will, then that's pretty much all you'll see. So you're going to want to go to Project, Project Wizard, hit Next a bunch of times, select the microcontroller you want to use, select the file you want to store, folder you want to store this project in, and that's pretty much it. Then, at one point, what you're going to want to do is right-click on Source File, Add File, and then import an assembly text file. Now, what I did was I wrote the initial code in assembly. The first time I did this, I wrote it using Programmer's Notepad, and then I imported it as a source file to MPLab. I'm having a lot of trouble with the camera. I imported it as a source file to MPLab by just hitting right click. That one's still there. By hitting right click, add files. And but now I don't even edit it in Programmer's Notepad. I just edit it in MPLab. So I guess if you wanted to start off your source files, just right click add file and then like bring in any text document and delete everything in it, or just bring in a blank text document or whatever. And that should be kept in the well, whatever. That's not important. On to bigger and better things like assembly. So again, as I told you in the last tutorial, I'm assuming you have some familiarity with assembly, or at least have used it before, because I'm not going to be going over the assembly language. I'm going to be going over how I use the assembly language to get my PIC 16 F870 on the spinning arm thing to do what I wanted it to do. So I might go a little bit more in depth than that, but you get the point. So basically, up here, what I did here is I just equated some names to some addresses, some register addresses in the microcontroller. So whenever I wanted to address the status register, I didn't have to say O3H. How am I going to remember that? But I can remember status, because that's what it is. So I did that for status port A, port B, port C. The tris A register, B and C. FSR is the file select register. That's going to be important for indirectly addressing a bunch of different registers, the general purpose registers in specific. Well, that's what we're going to be indirectly addressing to store. We're going to be storing data in the general purpose registers, and we're going to be indirectly addressing them to do that. So you're going to want to have a file select register there to save data into the general purpose registers. So basically the file select register points to a general purpose register, and any data, any byte that you read or write to or from, I guess, the location, the address 00H will be written to the register that that the file select register points to. So let's say you put 20H in the file select register. That's a hexadecimal number. 20 hexadecimal in the file select register. Any byte that you assign to lights or 00 or hexadecimal 00 for the address will be assigned to the register 20H. I also needed a delay, so I have a count for a delay that I'm going to be decrementing later, and then I have a counter because I needed another counter, I guess. I decrement something 9 times and then start back over. So basically right here I am going into bank 1 of the microcontroller. Right here this was the thing I mentioned in the other tutorial, and actually the electronics tutorial, the second one. When I was programming my microcontroller, I wasn't getting it to read the input from the Hall effect sensor at all, and I couldn't figure out what the problem with it was. So I decided to try a bunch of things, and for some reason, it would not read the Hall effect sensor unless I went to unless I set it as specifically a digital input. So I had to go and I had to set set all inputs as digital and not analog. You're gonna have to bear with me. I'm sorry. It is midnight right now, and I can't think straight, at least too much. So I'm trying my best. But you're gonna have to give me half a second because I need to pull up a data sheet for the PIC 16 F870. Because I don't memorize every single register in the microcontroller, and I don't recommend that you do. It's a waste of time. That's what data sheets are for. Alright, so the address of the register that you need to address to set all inputs as digital is 9F hexadecimal. So it's in bank 1. Obviously it has to be because I set all the inputs as digital after I went into bank 1. And 9F is addcon 1. So you want to address analog to digital converter 1 and set the 4 least significant bits of the lowest nibble, whatever you want to call it, of the addcon 1 register as 0110 in the PIC 16F870, and that'll set all port A as digital input output. Digital, not analog. That was the important part. On next thing. Anyway, so I set all bits of port A as output except for port A5, 0, 1, 2, 3, 4, 5. Yeah, port A5 is an input, and that's the one the Hall effect sensor is going through. Port C and B are all outputs because we need to be able to communicate with all the LEDs. I told you about this counter, this counter register that I had. I needed to. It's a general purpose register in bank 1. If you look at the data sheet here, we have general purpose registers in bank 0, which is going to hold all the information for like the LEDs, turning on and off the LEDs for the red, green, and the blue. General purpose register in bank 1 will just hold a couple miscellaneous things that we're going to need it to hold. One of them is counter, the other one is count 40. So an important note about that is every time we want to use these two registers, we have to switch to bank 1 first. You'll see that later on. So that's why I am assigning, I am storing a value of 9. I just did it in decimal because I was too lazy to convert it to binary into counter. So it's stored in that general purpose register in bank 1. I'm leaving bank 1. I'm just clearing port A, port B, and port C to start, just to clean things up. I am moving 20H and to the file select register. So the file select register is now pointing to the first of the general purpose registers in bank 1. You'll notice its address is 20H. And what I do is I move a byte into address 00, which I had the assembler equate to lights. So I'm basically moving this binary value, this byte, into 20H. I'm incrementing FSR, the file select register, so now the file select register is pointing to 21 hexadecimal. I'm moving this value into 21 hexadecimal. And I do that 96 times until I get to the last general purpose register, 7FH. So, a lot of copy and paste, and this is why I'm writing that code in Python, because drawing the image, which I showed the image of my spinning LED display to you in the last tutorial. I should have posted it on the same page. Changing these zeros and ones to display that image took me a long time, and that's why it is midnight right now. I videotaped that like 5 minutes ago. So basically, the order that I'm storing these in goes like this. So the spinning LED display has a column of 16. There's 16 LEDs in a column. It is a 16 by 16 display, and so I have port C control the top 8 LEDs and port B control the bottom LEDs. So what I do is I have the first file select register, 20H, control the top half for the red. Then I have 21H control the bottom half for the red. and then I have 22H control the top half for the blue, and then 23 hexadecimal, the bottom half for the blue, 24 hexadecimal, the top half for the green, 25 hexadecimal, the bottom half for the green, and then I move on to column 2, the second out of 16 columns. The top half for the red of the second column, the bottom half for the... You can't even see what I'm doing. Well then. Okay, so right here, I move on to the second column. This is the top half for the red of the second column. This is the bottom half for the red of the second column. This is the top half for the blue of the second column. This is the bottom half of the blue for the second column. And I continue that, again, 96 times, all the way to 7FH. This part of the code is a lot shorter. That's all there is. And this is what actually makes it work. So right here, I just labeled this just for the assembler as start, so it can jump back to here every time I call that. What I did, the first thing I did, because the first thing I want my program to do is wait until it gets an input from the Hall effect sensor. So bit test the following register, bit test the whatever following skip if set. So it's going to be testing port A bit 5. That's the input for our Hall effect sensor, and it's just going to keep it's going to test that, and it's going to say, okay, well, are we receiving an input? No, then don't skip. It'll just go to start. Bit test, are we receiving an input? Still no, don't skip, go to start. Bit test, are we receiving an input this time? Yeah, maybe we are receiving an input, so it will skip down and do the next thing. I clear the status register bit 2. I'll explain why that's important later. That's the 0 flag in the status register, and you'll see where that comes in later and why I need to clear it here. I start off by having my file select register point to the very first location, because that's where I initially want it to that's where I want it to start. I don't want it to start drawing the image in the middle. And then this is where I begin to draw. So I set port A0. So what that does is that sends a signal to the TIP31 transistor to allow all the red LEDs to go to ground. Because I believe I explained earlier they're common anode LEDs with 3 separate cathodes, one for red, one for green, one for blue. So MOVF lights 0. I'm taking the byte from lights. I'm not erasing it from lights, but I'm copying it to the W register, the working register. Then I'm moving that value from the working register to port C. So it's then sending the data for the top half of the red LEDs in the first column to port C. It's going to increment the file select register, and then it's now looking at the bottom half of the LEDs, of the red LEDs in column 1, and it's going to send that to port B. It's going to call a delay before I turn either of them off, because otherwise this clock is running at 20 megahertz, and I believe it's 4 clock cycles per 4 clock cycles per instruction or something like that. But either way, it's ridiculously fast. So if I didn't have this delay here, the image would be really scrunched, and that would be a problem. So I call a delay, jumps to delay down at the bottom. As I mentioned before, every time I want to use a register that I have in bank 1, I need to switch to bank 1. So I told you count 40 was in bank 1. And I'm going to need that for the delay, so I bit set the following register, status bit 5, and now I'm in bank 1, so I'm going to move the decimal value 40 into count 1. I'm going to decrement that, skip if 0, but it's not 0 for like 40 times, so I just keep jumping back up to loop with this go-to command. I'm going to, once I leave the loop, I'm going to bit clear the following register, status 5. I waited enough time. So I'm going to go back to bank 0, and I'm going to return back to the piece of code I started from. And during that delay, I already told you before, the top half and the bottom half of the red LEDs were lit. So then, the reason why I have these two, I believe it stands for no operation, but either way, it's just a time waster in this instance, these two commands. The reason why I put them in here is so that the top half of the LEDs and the bottom half of the LEDs are on for the same amount of time. I realize it's a small percentage of waiting 40 plus cycles down here in the delay, but I still wanted to ensure that the top half and the bottom half were on for the same amount of time, so maybe the top LEDs wouldn't be brighter than the bottom LEDs, or appear as such, due to pulse width modulation. The reason why I put 2 in here is because there are MOVWF port C, 1, 2 MOVWF port B. So I needed to turn off port C, wait 2, then turn off port B, so they would each be on for the same amount of time. Then I'm going to bit clear the following register, port A0, and that concludes the red. That's all for the red LEDs for the 1/10 of the times it's going to blink for the first column, for the first draw. I had to put a bunch of no operations in here because if I didn't, the TIP31 transistor, for some reason, it would not shut off. It would not shut off current from the collector to the emitter fast enough, even when I pulled current from the base. It would not shut off fast enough to keep the red LEDs from being on when blue was on. I believe this next set is blue. So the blue would be blue with red if I didn't have all these no operations in here. Then I did move on to the blue. I did the exact same thing for blue. So this port C is doing the first time around, or for the first column, it is 20, 21, 22 hexadecimal is the location the file select register is addressing, and port C is drawing the top half of the blue LEDs in the first column, and port B is doing the bottom half of the blue LEDs in the first column. I do the exact same thing for blue as I did for red. I bit clear the following register, port A1, so then I turn off power going to the TIP31 transistor, connecting the blue LEDs to ground. I do the same no operation deal, and I do the exact same thing for green. I don't have a bunch of no operation at the bottom, commands at the bottom of this section for green here, because it has to go through all this other code, and that's enough time for the transistors to, I don't know what you would call it, a propagation delay or whatever, but that's enough time anyway, whatever it is. So I actually didn't need to label this here, but I did. I labeled it advance because you could potentially be advancing to the next column, but you might not be. It's kind of tough for me to explain this. I'll try my best though. So in order to, because I told you in one of the previous tutorials that we'd be flashing the red LEDs one time around the loop, the blue LEDs another time around the loop, and the green LEDs another time around the loop. So one color per time around the loop. Well, that ended up not working because I'm not spinning this thing fast enough to do that. So I do have to flash them on and off multiple times within their column on the same time around the loop. So that's what this did. This just flashed them on 1 out of their 9 times, or 1 out of their 10 times, in the same column, the same time throughout the loop. So what I have to do is I have to first see if it's gone around 9 times or not. So at the very top of the code I set counter, or I stored a value of 9 into counter, but remember that's in bank 1, so first I have to switch to bank 1. I decrement counter, I skip if 0, 9 out of 8 out of 9, 9 out of 10 times, whatever, it's not going to be 0. So I'll just go back to same color. Same column. Same color would be a rather inappropriate name for what it's doing. Same column. So if counter is not 0, it'll still be drawing the same column. So I jump down to same column. I switch back to bank 0. Basically I subtract 5 from the file select register, so the file select register is back pointing to the first one, the red top column, instead of the green bottom column. and I go back to draw and continue the sequence, or I continue whatever it was doing. Now let's say counter is 0, then it's ready to move on to the next column. So what I do is I first store 9 back in counter, so counter's reset and ready to go. I jump back to bank 0 so I can deal with the file select register. What I do is I take the value, the address pointed to in the file select register, which is a binary value. I can perform math on that address, I guess you can say. And then I'm going to do a subtraction. So I move that value of the file, what's in the file select register, into W. I perform a subtraction between that and the literal value, this here, hexadecimal 7F. And that is, if you remember, the maximum value in the general purpose register. So that is the address of the highest address, I guess, general purpose register. That's the 96th byte of general purpose registers. So this here, if that is 0, so if I am at the very highest general purpose register, I don't want it to keep adding 1 to the file select register. That'd be meaningless, and I don't even know what would happen actually beyond that point. So I test to see if file select register is at the very highest. If it is, the status 2 will be set. That's the 0 flag. The 0 flag will be 1 if any logic operation or mathematical operation or whatever, or most of them at least, result in a 0. So skip if clear. So if it's set, I want it to go back to start. And if you remember at start, I told you I clear the status 2 flag. Well, that's to reset the 0 flag for next time. And by jumping back to start, I also start the file select register back at the beginning, so I could redraw from the beginning. Now let's say the status 2 flag is not set. It's clear, which it will be most of the times. It'll jump down to here. It will add 1 to the file select register and begin redrawing. So basically, if the code makes it past same column here, after this decrement the following register, skip if 0, it will definitely redraw a new column. But then this here, the subtraction, the bit test, the 0 flag determines whether it will draw the next column, or maybe if it is already done with the 16th column, it'll wait until it picks up the Hall effect sensor and then start redrawing the image all over again from the beginning. So the reason why I add 1 here is because throughout this whole drawing sequence we incremented the file select register 5 times to go through red top, red bottom, blue bottom, green top, green bottom. Well, to get to the next red top for the next column, we need to increment the file select register 1 more time. So actually, this piece of code here was kind of useless. I don't need to move the literal value to W, binary 1, and then add that to the file select register. You could just type increment the following register, file select register. So that would work just as well, and it's better, I guess. So yeah, I just wrote up this code a couple minutes ago, so I probably should clean it up first, but whatever. So then it increments to from green bottom to the next column red top, and then it begins drawing. And that is basically all there is to this code here. That's basically how it works. So it's 12:12 morning, 6 hours till I gotta get up for school tomorrow. Sorry if I wasn't terribly clear on this. I tried to explain it the best that I could. I will be posting this on my website. I will also post, when I finish, a copy of the Python code, which you will need a Python interpreter in order to be able to run. It'll be Python 3.2.5, and I am using that Pygame library for the graphics and stuff like that. So I'm not going to, well, I could include some text on how to download those, but I'm not going to be making a video on that, as that's not in the scope of any of these tutorials. But either way, I hope I was able to help some, at least, on this assembly code programming. I will be posting this code on my website, so thanks for watching, and I hope you enjoyed this tutorial series. Oh, one last thing. It probably wasn't very good of me to just start up the camera like this, because now I'm not very good at video editing, and I'm going to have to pin these two video segments together, and that won't turn out well. But one thing that I completely spaced out on, I forgot to tell you guys, it's late. Man, I can't think straight. Is taking this assembly code and then putting it onto the chip that you have, which it's not actually like. Alright, so what you're gonna have to do once you write your assembly code as is a source file in your project, file, save. I can't save because I didn't make any changes, it's the same. You can't even see what I'm doing, so great. So save was kind of self-explanatory, everybody knows how to do that. File, save, project. You're going to want to go down to build all, and if you did it correctly, you should have like a bunch of messages, maybe a warning, but no errors. And it'll even have blue. If it's red, that's bad. Blue is good. Blue, errors, 0. Then go up to the top, programmer, well actually it's not selecting a programmer because I don't have one plugged in right now. I am using, wow, that zoomed in way too far. I am using a Picket 3 programmer. It just connects actually to those pins that we soldered in, or I soldered into my board. I showed you the connections for them in the schematic, which is also posted on the same page as one of the previous tutorials, and just connects to the computer through USB port. So I'm going to plug it in, and the software will, I think the first time you have to select a programmer, but then after that it'll just connect to the programmer, and it'll try and read the chip that you're using for the project that you're currently working on. So it should say make sure the device is actually connected or something like that. There it is. It'll say check that the PIC16F870 is actually physically connected, which it's not right now. I just plugged this in. So the next thing you're going to want to do is actually get your persistence of vision display. Alright, you're going to want to get your persistence of vision display, and just plug the Picket 3, or you could be using a Picket 2, whatever, into the circuit board right there. The connections, again, I have on the schematic. Hit OK, whatever, it's connected, and if it worked properly it should say device ID revision, then a bunch of numbers. Then you can go up to programmer, hit program, and it should say programming and verified complete, and then your chip is programmed and ready to go. A few things. I told you, I'm assuming you've used MPLAB programmed in assembly, stuff like that. It's not really a tutorial on how to use this, but there is one thing I did want to mention. The Picket 3, actually this is another thing, but this really wasn't what I was thinking about a minute ago. The Picket 3 requires that you power the chip either from an external source or select specifically that you are powering it from the chip. So in order to select that you're powering it from the chip, which I can't even, in order to select specifically that you're powering it from the PICKIT 3, as opposed to from an external source, which you could do both, whatever, I don't care. But to select the powering it from the PICKIT 3 so you don't run into future problems, configure settings, and that was not even it at all. So you want to go to Tools, Programmer, there we go, Programmer Settings, Power, and Power Target Circuit from PICKIT 3. And that's what you're going to want to do. Hit Apply down at the bottom, and then OK. The thing that was more important was, I forgot which pin it was. It's late, but if you remember in one of the previous tutorials I told you I was having trouble getting one of the LEDs from, I believe it was port B, to light up. Well, that particular pin was involved in some sort of low voltage programming thing, which I've had no experience dealing with, at least not in any of my projects so far. I'm not really familiar with it or anything like that. I just wanted to use it as an input-output. So I fixed that basically by going into the configuration bits, which you can set in code. I don't. I just go up to the top of the page, hit configure, configuration bits, and it's this one right here that you want to worry about. LVP, low voltage, RB3, so I guess, yeah, it is port B, I guess the fourth pin, 0, 1, 2, 3. Yeah, so just select, this is a problem with MPLAB. I can't see the entire drop-down box or even the entire drop-down prompt, but it's the bottom one that you want. That will disable the whole low voltage programming thing, and you'll be able to use it as a standard input-output port. So yeah, that's pretty much it. I hope what I said was somewhat coherent and you're able to get at least the gist of it. So thanks for watching. I hope you enjoyed this series.